There are three types of energy that we quantify in Year 12 physics. There's a kinetic energy, which is equal to a half mv squared, gravitational potential energy, mass times gravity times the change in height, and strain potential energy, the energy stored in springs or elastic materials. It's half kx squared, where k is the spring constant. And we move between these forms of energy all the time. We lose gravitational potential and gain kinetic when we fall from a height, for instance. Or we launch something with a spring, and so we lose strain potential energy and gain gravitational potential. And so we change between these forms all the time, and every time we do that we're doing work, or something is doing work. Anytime energy is changed from one form to another, or from one body to another, work is done. In reality, some energy does leak out every time it's changed through friction, heat loss. We tend not to consider that in a quantitative way so much. So one of the ways that we think about work is the gain or loss of energy by a body, or the exchange of energy from one body to another. We also define work as force times displacement. So when a force moves something through a certain distance, it's doing work on it. It's important that force and the displacement are in the same direction. They are both vectors, of course, so you may often see this summarized as W equals Fx cos theta, where theta is the angle between the force and the displacement. So obviously if they're in the same direction, theta is 0, cos of 0 is 1. If they're at right angles, the cos of 90 is 0, and so there's no work done if the force and displacement are at right angles to each other. So here is a car moving with some kinetic energy to the right, and there's a frictional force acting against it. The car will lose an amount of kinetic energy equal to the force that's applied by friction times the distance that it acts over. So, for instance, 100 newtons of force acting over 2 meters will mean that 200 joules of kinetic energy are lost, and so you could use the formula of a half mv squared to work that out, to work out exactly how much velocity it had lost by considering the kinetic energy here and the kinetic energy at some time later when it has lost that 200 joules. Now, once every semester we have trial exams printed for our physics students, and they arrive at the bottom of the Carney building down here in big boxes, and I reckon those boxes weigh about 50 kilograms. And what I often find myself doing is carrying them up the stairs of the building, up to the 5th floor labs to be distributed to students, and I think that's about 12 meters vertically. And I often think to myself as I'm doing this, how much work am I doing? How much energy am I expending? Because it feels like I'm doing a lot of work. Well, we can estimate that by a number of different means. We know that work equals force times displacement. And so, again, remembering that the displacement is in the direction of the force, of course the gravitational force acts vertically downwards, and so the displacement we need to consider is the vertical displacement. So even though I'm walking backwards and forwards up these flights of stairs, it's this vertical distance that we need to consider. So the work that I'm doing is the force that I'm applying. Now, to lift these boxes, I'm applying a force opposed to the weight force, so 50 kilograms times gravity is 500 newtons times the displacement 12. So I'm doing 6 kilojoules, 6,000 joules of work. Another way we can calculate this would be work as a change in energy. So the work could be the change in gravitational potential energy. So these boxes, by being lifted up to the 5th floor, are gaining a certain amount of gravitational potential energy. So if we define their GPE down here as 0, then the gravitational potential energy will be their mass times gravity times the change in their height. So the gravitational potential energy they gain is 50 times 10 times the change in height is 12. Of course, because work and energy are both scalars, it's irrelevant whether we define gravity as positive or negative 10. And so you can see again, no great surprise, that's 6,000 kilojoules of gravitational potential energy gained by those boxes. And that's the amount of energy that I've expended getting them up there, the amount of work that I've done against gravity, which is actually about 10% of the energy in a spoonful of sugar. Just something to think about, quite insignificant really.